Good evening, WR514. My name is TR Heidman. This is my final project using GIS analysis to identify water monitoring locations at a field site being operated by the Native American Cultural Center. So what is the NAC? The NAC, as we call it, but it's Native American Cultural Center. It's an organization at CSU. They've been around since the late 70s and offer a place of support for different students, tutoring for everyone. Everybody's welcome for that. Schedule the powwow each year, and then a bunch of events during Native American Heritage Month. So recently, they came into a large property, 70 acres, donated by Paula Huddleston, uh, very wonderful person. And so this is intended to be a site of research, fellowship, maybe a retreat someday with limited lodging, some lab areas, a phenology walk, different uses for native plants and forageables, um, and especially just a place to for individuals to learn about other cultures and backgrounds, and to host other schools that have these similar type programs. So the property is it's two parcels. So if you look at the picture over here, the western side, that's where houses and utility buildings are, and then there is seasonal grazing livestock. So there's a little bit of soil compaction, but there's an enormous cliff that runs to the north side of that, what looks like a river in this picture. And then on the east side, it's relatively uh, undeveloped, underdeveloped. The animals don't graze there. It's left kind of in its current state. And then that yellow circle down in the bottom corner, there's evidence of some sort of retention pond at some time. There's an earthen berm that washed out, and it no longer holds water. So just kind of remember that spot down in the corner. So what we're doing is we're looking at this area for opportunities for restoration and to restore the riparian ecology. What looked like a river in that picture is actually this dry ditch that has not held water in quite some time. That's here in the middle. Wish I had a better picture, but it's like waist deep, dried, kind of overgrown. And there's some evidence further down the hill around the property owner's home and around the buildings of these like crude dams, like over here on the left, and there's also some concrete and rock ones. And we think that was to kind of divert and retain water and maybe wash out a bigger area for the livestock. There are sources of water that we've noticed. So runoff off those cliff faces, that's the picture over on the right. Seasonal snowmelt and precipitation events cause this like trickling. So here's sort of what I was saying about um, what's progressed over the last, what is this, 30 years. So the top picture is 2014. This is the Wayback Machine, Wayback Google by Esri. And so if you look at the bottom picture, which is currently, you just notice like both waterways, which North Fork Rabbit Creek is actually south of her property. She lives right across the road, but it is even if you look at like the stream in the bottom picture, in the top half of the bottom picture, you can see how overgrown that is, just in 30 years. So the hydrology's changed, the ecology's changed, and as a consequence, vegetation has, right? So what we want to do is we wanted to identify where these water sources are coming from so we can begin to quantify what we've got there to see what kind of restoration we could do. Could we plug up that retention pond? Could we restore those stream banks? Haystack Gulch is the name of that river that runs, that river bed, that channel, Haystack Gulch that runs through the middle of the property. So, we just start off by knowing where the water's coming from and maybe how much we've got. So there's something else I've started studying and learning about is these IRES, intermittent rivers and ephemeral streams, and these are usually seasonal streams driven by snow or precipitation. And it's estimated they drain half of the Earth's land surfaces, which is pretty incredible to think about. Some of them may only occur for a few days, up to like weeks, or maybe just off and on, all throughout the year, which is a little bit what we're seeing. So there's a growing interest in this for climate resilience and just learning about these processes in our drought, water stressed world. So what I want to do was do a kind of a simple analysis model of where these ephemeral streams are occurring. That's flow chart over here on the right. So starting with a high resolution DEM, you determine flow direction, the flow accumulation. Those are different math formulas for the way that it moves across pixels. And then from automatically created pour points, I ended up delineating where the streams are. But then the step that I took it further was this stream order, which is the first time I used this tool. And it's an algorithm, it's a calculation that you can determine either how many tributaries go into one of these little channels, or how large the area is that drains into it. So you can kind of determine like which of these happen, for more than a day or more than a few minutes. The higher the order streams. And so that's the first analysis that we did. So here's that high resolution DEM. That's 1 meter, so it's LiDAR, which is really cool. The regular government stuff is 30-meter square resolution, so this is 1 meter. We recently got LiDAR as part of a USGS program. It's available for free, but in a lot of areas of Colorado just of this year. Um, yep, so start with DEM. And you can see that channel. So this is a bare earth DEM, the channel that runs through the property through the middle. Okay, and so this is with the flow accumulation and flow direction tools layered on top of each other. And so what it does is it determines from pixel value representing elevation going down into these creases and folds of the earth. So all these areas are points of drainage. I mean, that's like every possibility. And so here's just cleaned up a bit and just delineating one line into each of those channels. So that's the whole max site. This is the entire modeled runoff for the iris. And then here's after the slope, or sorry, let's see, what is it? Stream order tool, which I basically cut it down to the ones that had the most significant amount of flow. And you see how that lines up like perfectly with the slope on the DEM there. And so the darker ones, those lines, those are the intermittent ones. And then Haystack Gulch is that river ditch that runs through the middle of the property. And then you notice at the top I said like hybridize with the USGS model. So I went and I checked it. I went and just downloaded the data set that is available to all of us and laid it on top, and they matched up pretty well. So the next thing is like, where do we put, now that we know where these things occur, where do we put the monitoring stations, to understand these processes on the land? So we determined there's two different things that we're monitoring. Okay, one is the iris flow, like those 3 points on the map that may only occur for a few weeks out of the year. And then the other is within Haystack Gulch, upstream, middle stream, downstream, to determine how much water like does run into this channel, how much water pools there in the summer. Is it, if we plugged up that pond or we did some other cleaning out the channel, like is there enough water still occurring on the property? How long would it take to fill these bodies, restore the riparian environment? So two different monitors. That's the point here. The first one is just a binary yes no, and we're doing that with either temperature or electrical resistance. That determines when the water is occurring, and then we're backing it up redundancy with game cameras. And that's what I have out there right now. So I've got game cameras. That's how I sort of found what these are doing. And same thing if you look over here on the right. So that's in Haystack Gulch. That's the second type of monitor, monitor B. And we're looking at water in the channel. So I left a post. This is the first iteration, and then that's a picture from the game camera. So start off, I mean, we're doing the waterways, right? Until we need it uh, within distance of the waterways, because the game cameras over really over about a meter, and they get murky, but definitely 2 meters. We wouldn't capture what we're after. So everything was done within 2 meters of the waterway. So that's what this is representing. So the type A, which measures, the yes, no occurrence in binary. So what I did is you take the DEMs, we needs to be on slope that's less than 8.5 degrees, and then aspect that is not, this is kind of fun to think about, that was not facing east or west, because when the sun rises and sun sets, it would just completely wash out the lenses of the cameras. So they needed to be north-south, preferably. And then combining that with the buffer of the river. So here's the ran the slope tool, and then here's me reclassing in binary everything below 8.5 degrees. Look over to the far right, it says like start in new. You can see I've just got the ones and zeros, so I kept everything 8.5 degrees and under, and eliminated the other. And pretty much the same thing on aspect, except it was out of 360 degrees, which is kind of cool. So I had to think about what was east and west as far as degrees goes, so 90 and 180. I haven't, this is the reclass. It doesn't look like I've typed it in yet, but that's what went there. And we actually left, kind of a on each side, not just do east-west. And then turn each of those, the binary yes raster reclassifies into polygons, so you can run the intersect tool. And so that's just all these layers laid on top of there. Right now, just kind of looks cool. So this is uh, not quite the final analysis, but this was every piece, every pixel on the property that met these conditions um, without the river buffer, right? So they're just this is everything that fell into that. Just looked really cool on top of that slope picture. Again, can make a good visual. And so now what this is it's clipped just to those three ivories, those three intermittent rivers. So what this is saying is anywhere along those yellow points, of course, go in the field and investigate, see what kind of surfaces you have and things like that. But that's what the model is showing. And so now the next type is stream depth, um, which is just in Haystack Gulch. So we want to find the deepest parts, where water is more likely to pool, and so we can monitor that water level. We don't just choose a site that is, high up that is drained all the time. So the top half of this flow chart is the same thing I did for the last analysis for the type A, but this just takes it a step farther with at the bottom of the screen. So what we're doing is we're extracting the DEM along the river's path. It's the bare earth DEM, so we know the depth of the water channel. And we're only taking the deepest part. So here is every point along that river that met our suitability that was in Haystack Gulch. That's not really what we're looking for. There's way too many points to mess with. And so here's what we're doing here, extracting that DEM by mass, which is the tool to just take the river part. And then I'm taking a step further. This is the first time I did this. And so I broke it into quantiles and chose just the lowest. And I'm over here, I'm setting it binary once again, choosing the lowest range is good and everything else eliminated. And so this gave me, oh, my picture's right on top of it. But anyways, that's the lowest point of the properties down there in the corner, which that doesn't give us, it is the lowest point. That's what I was asking GIS to do, but that doesn't answer our question of finding the deepest points relative to their other pixels, which is, I had to kind of think my way through that. And so what I did is I played around with the raster calculator and the near pixels doing a like standard deviation from nearest pixels. Really cool tool. I didn't know what I was doing, so I just guessed and checked. I just put in different ranges. And so this was the tallest point of the property. So when I made it that exaggerated yellow or that lighter blue white color, that let me know that I was like finally figuring out my ranges. So here's what I landed on for the lowest points relative to their neighbor pixels along Haystack Gulch. And so, based once again on Earth's surface and things, but this is places that should pull water. For the longest, water should pool there. So this is the good locations for our Type B monitors, which monitor water depth. Just breaking down one last step is we wanted to capture upstream, middle stream, downstream, see how much water is coming in, see how much water is at that deeper part, the part that was manipulated with different dams, and then see how much of the water that enters the property upstream ends up flowing out or down towards that drainage area where that pond used to be. So yeah, final analysis for the Type B monitors. And so there's kind of this is the end of it, but here's me out verifying those sites. Here's GPS positions pulled from that analysis, the water runoff, and here's my updated stake, which can be seen by a little bit farther with the game camera based on the colors. Maybe I can extract pixel values for the next part of the study, but special thanks, Native American Cultural Center, Paula Huddleston, and my laboratory. Great people.